Okay, so the solution here is, okay, at constant pressure where you have this key result where delta H is Q plus non-mechanical work. So again, we can just sort of use this. There's no non-mechanical work here. We can envision just doing this process, by doing it just sort of using a, flowing heat to and from the surroundings. We don't need to envision any non-mechanical work. Under these conditions, we have delta H is equal to Q, which in it is a reversible process. So we can say delta H is Q rev, and therefore we can say delta S is, since Q rev is delta H under these conditions, delta S is going to be delta H over T. Okay, now since we have a reaction here where this delta H is delta fusion H, we just add those subscripts on. So delta fusion S is equal to delta fusion H over T. Again, important to note here that, so delta RH determines delta RS for phase changes, since they can be done reversibly, but for most chemical reactions, we can't just determine the change in entropy from the change in enthalpy. Usually this equation doesn't hold. It only holds here for sort of phase changes, right? This would also work for vaporization. And again, you can replace it with all the other ones, sublimation, all the other normal phase changes where we can do these processes at equilibrium will work. Okay, here's a nice example. Using the equation, we can get the delta H fusion, delta fusion S for ice melting. Okay, using the equation, units-wise here, it's useful when we plug in to go to joules. So this is 6010 joules per mole over 0 Celsius is 273.15 Kelvin. We always need to use Kelvin in here. And our final answer is 22.0 joules per mole Kelvin. Okay, so here we have the molar heat capacity of water from 0 to 100 Celsius. What is delta H bar and delta S bar for water between 0 and 100? So what will delta H be and what will delta S be using the heat capacities? Okay, so from the last set of slides, we have these nice relationships at constant pressure where we can get delta H and delta S directly from the heat capacities. So these are the equations we had on the summary slide last time. We're interested in molar, so again, we can stick molar in front of all the extrinsic functions, and that will still work perfectly fine. So for delta H, we'll need to integrate Cp. For delta S, we'll need to take Cp divided by T and then integrate it. Okay, here's the solution. Again, here's some derivation there if you want to see it again. dH dt at constant pressure is Cp, so this gives us delta H as Cp of T dt. We integrate using our normal integral rules, get 7549 joules per mole. And again, since d bar q rev is Cp over T, we can get that. Again, same equation we got. When we plug that in, we get 23.55 joules per mole, right? We have to divide each of these by T, then integrate. We're going to get a term here with ln of T in it. Again, you can do it by hand, but just as easily, I would say this works great in Python. Just type it in using SymPy, and it works very easily. So here are both of those calculations using SymPy. This is using the js.munano.org, or feel free to just use the SymPy notebook from the previous homework assignment. But yeah, here it is, sm.integrate Cp from 273 to 373, or sm.integrate Cp over T from 273 to 373, and that gets us both of those answers. So SymPy works great for these type of problems.